graycode. So we came until number systems and codecs. Number systems, we talked earlier about decimals, binary. Here we stopped here. We create them. Binary. Computer. So actually, we completed here. The next series we have end up. These are all I already covered in my LinkedIn page and now PMX will feed in later. We will study number systems. This means, for example, for decimal 10, 0 to 9, binary 2, which stores 2 elements 0, 1 option, auto values 0 to 7, hexadecimal 16 values 0 to 9, and due to acceptables 10 to 15. Decimal, this is the more normal number system we use. For example, 538 means 5 into 10 square plus 3 into 10 plus out 10 4 0. This is map we can see. It is zeros, ones, twos, 10 square. Binaries, computers and digital circuits use 0 to 1. Example 1011 base 2. Each position represents a power of 2. Here, think of this as an 8421 code. 2 power 0 means 1, 2 power 1 means 2, 1, 2 power 2 means 4, and 2 power 3 means 5. If you see this in 8421 code, then this 1011 value is 5 plus 2 plus 8 plus 2 plus 1 is 11. So this 1011 code is 11. You can see 11 base 10. Decimal binary use repeated division by 2. Example, that means it is not just an 841. If it is even large, we can increase it by 2 power 1, 2 power 2, 2 power 3. Here we can put 2 power 4. If 11011 value they ask, we can put 2 power 4 16 like calculate that. Decimal binary use repeated division by 2. Example, 13 to converting a decimal number into binary number, we need to we divide 13 by 2. If 6 comes, remainder 1, then you need to again divide by 3. If remainder 0, then you need to divide it until remainder 1, remainder 2. You can't divide it anymore. So we got remainder 1011, real remainder bottom to top 110. So we need to 1101 from bottom to top, we need to write when converting 13 to decimal binary number. After base height, distance 0, 1, 2, 3, 4, 5, 6, 7. Example 157 base height means 1 into 8 square plus 5 into 8 square 1 plus 7 into 8 power 0, 61 plus 40 plus 7, 157 base height equals to 111 base 10. So if we add this 7 plus 0, 7 plus 4, 8, 9, 10, 11. We get 11 and 6 plus 4, 10 plus 1, 11. 11 base 111 base 10 we get. So easy, simple. Hexadecimal, converting a base into, we need 16 symbols for the after 9 we need bracket. For example, 2F16, converting into decimal. Here F means 16, 2 into 16 plus 50. What the hell? Hmm. So Don't get confused here. Here 2 and 16 means look it as 16 power 0, 16 power 1. Here we divided f into 16 power 0. F value is 15. We calculate f value is 15. Okay. So 15 into 16 power 0 means 1. Then 15 plus 15 into 1 is 1. 2 into 16, 32 plus 15, we get 2 of 16 equal to 45 this time. Binary converted into octal. This is very useful because uh, it equals to 2 power 3. Therefore, groups binary digits in three uh, sets for from the right. Example, here 101, 101 base 2. Here 101 is a set and 1011 is a set, two sets. 1011 value in binary is 5. So we get 5 5 by 6 even octal to binary we get, sorry, we converted binary into an octal using the logic it equals to 2 power 3, 3 sets. This is one set, this is one set. So we converted as 55 by 6, binary hexadecimal. Binary conversion to hexadecimal. Since 16 into plus to 2 power 4, group binary digits in 4 sets. Here we converted 4 sets. 2 power with 4 is 16. Same way we done this. We got 1011 value. It gets I plus 2, 9, 10, 10 plus 1, 11, 11 value is D for the hexadecimal. So binary is converted to hexadecimal. This is the 16. Now codes. A code is a way of representing information using binary patterns. Different codes are designed for different purposes. The important ones for your syllabus are BCD, graycode, AC2, access 3, and then we'll connect these to error detection or correction. BCD, binary coded decimal. BCD means binary coded decimal. Each decimal digit is separated represented using 4 bits. For example, 59 base 10. Don't connect 59 directly to binary. Instead, 5 is converted to 4 binary bits. 9 is converted to 4 binary bits. Therefore, binary code digit is 59 base 10 equals to 0101 1011. Compare that with ordinary binary. 59 base 10 is converted to ordinary binary 111011 base 2. They are not same. Important because important BCD uses 4 bit per decimal digit. Gray code. So this is binary coded decimal. It converts each digit into a binary number, and this is a binary code decimal. This is a code. Gray code. Gray code has an important property. Only one bit changes between consecutive values. Uh, for example, this is binary 0, 1, 2, 3, 4, 5, 6, 7. Here 0, 1, 3, 0, 1, 3, 2. What is I don't understand what is growth. Only one bit changes between consecutive values. 0, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7. Notice 0, 0, 0 converted to 0, 0, 1. Only one bit changes and 0, 0, 1 is converted to 0, 1, 1. Again, only one bit changes. Why is that useful? It reduces errors during transitions in systems such as rotatory shaft position encoders, digital measurement systems. So in binary, we will say 0, 0, 0. In gray code, it is 000. In binary, we say 001. In gray code, it's 001. In binary, this is 2. In gray code, this is 2. In binary, this is 3. In gray code, this is 3. Like he is adding the numbers. Here 1, here 2, here add, here 1. Then this becomes 0. I don't understand. Yes. Mm. Here it is a consecutive order. If we look at it as 0, 1, 11, 11, here it is uh, let's come to this letter. Access 3 code. Access 3 represents each decimal digit by digit plus 3 and then converts that result into 4-bit binary. Example, decimal digit 5, add plus 3, 5 plus 3 equals to 8, convert 8 to 4-bit binary, 1000. This is access 3. So 5 is converted to 1000. Access 3 for 2, 2 plus 3, 5, it is access, it is represented as 0 and 0. ASCII, ASCII stands for American Standard Code for Information Interchange. It represents characters using binary codes. For example, characters such as A, B, C, 1, 2, at the rate, each have a numeric code. A classic example, A equals to 65 base 10, and in 7-bit binary, 65 equals to 10000001 base 2. Pi value is very converted it into binary, decimal to binary. How to convert decimal to binary? Decimal to binary, we divide it by 2. We divided this value by 2, you will get 10010. So computers can represent text using binary. Important comparison code main area BCD each decimal digit 4-bit binary. Gray only 1 bit changes between adjacent values. Access 3 decimal digit plus 3 will represent binary. ASCII represents characters. One thing to be careful about binary is binary number is not equal to BCD representation. For example, tower based on the ordinary binary 1102, BCD is 001 or 0010 because BCD represents 1 and 2 separately. The next item in my syllabus is algebraic. Gray code 01 1 1 1 0 5 1 gray code. Gray code is a way of representing numbers so that when you move from one number to the next, only one bit changes. Let's say 10 times plus. Compare normal binary. This is normal binary. We know. Look at 001 is 0010. 010. Look at 001, 0012, 00010. 2 bits change. Both changed. 0 is converted to 1, 1 is converted to 0. And 3-bit changes. In here, 0 onto 0. And 0, 112, 100 is, for this value we get both change, that's why we get 10. And here 011 to 100, 3 bits change. So here 001 to 100, here 3 bits change. 1 is converted to 0, 1 is converted to 0, 0 is converted to 1. Gray code represents gray code for 0 to 7 is 001, 001, 011, 10. Now look 001 to 0002 001. Only one bit changes. Then 001 to 011. Only one bit changes. Then 011 to 010. Only one bit changes. Then only one bit changes. Gray code edges and numbers differ by only one bit. But why do we need this? This is the important part. Imagine a sensor is changing from one position to another. Suppose normal binary changes 011 to 100. Three bits have to change simultaneously 011 converted to 100. But in a real electronic circuit, the three bits may not change at exactly at the same instant. For a tiny moment, the circuit might see something like 011, 010, and could interpret one of these temporary values incorrectly. The record avoids this instead. The transaction might be 010 and converts to 110. Only one physical bit needs to change, therefore the probability of transition errors is reduced. Think of a rotating wheel. This is one of the possibilities. Imagine in a rotating disk, we are going somewhere. We just want to know what is it. It only changes on the. Then why here 001 is one converted to 010? Here not here one bit only changes. Right for the here not here. 0102. Exactly for decimal 2 and 3. Only one bit changes. So ordinary binary can also have one bit change in some case. The difference is that binary does not guarantee this for every consecutive number, whereas gray code guarantees this compared to the next transition. So that's the thing. Ordinary binary also can have one bit change, sometimes two bit change. It has both two bit change and one bit change, but of gray code it is only one bit change. That's the difference. So gray code look at here one bit is changed. Here one bit. Here also this is same. Here one bit is changed, and this is changed. Here one bit is changed, and these two are same. And here one bit is changed, and these two are same. Now it is here one bit is changed, and it is now same. Now these two are same, and here one bit change. Only one bit change. You can look, only one bit is changed. How to remember? I don't. 00 0000001. That's a very good. How to remember very good. This time. Use one rule. Think gray code story. Gray code only one word changes with another number. binary 0012 100 3 bits change here. Like if we take two numbers from top, we can understand how the graph works. If we look at this before, if we take these two, here 0 is converted to 1. If we take these two, here 1 is converted to 0. If we take these two, here 0 again is converted to 1. If we take these two, here 1 is converted to 0. Look at it, it is binary. Here, if we take first two parts, 0, 0, 0, 1, 1, 1, 1, 0, the remaining are changing here. That's how we can remember that. From 0 to 0, 1, 0. For example, binary converts to graycode. Then 1 XOR 0 equals to 1, 0 XOR 1 equals to 1, 1 XOR 1 equals to 0. You'll get first order here. 1 XOR 0 equals to 1. 0 XOR 1 equals to 1. 1 XOR 1 equals to 0. Then you get the boundary code 110. Hmm. Okay, what's next, guys? Error detection and correction. I have covered this cycle. Let's start error detection and correction. What is an error? Digital system transmits bits, sender and receiver and this. Ideally, the receiver gets exactly what was sent, but noise interference can cause a bit to exchange. Sorry, bit to change. For example, sent 10 this value, received this value. Here we get an error. Error is this. Here we get an error. The sender transmitted 1, but the receiver received 0. Here we get error. This is called a bit error. The digital systems only receiver gets exactly what was sent, but because of the noise and interface, can cause a bit of change. This is called a bit error. Why does this happen? During transmission, the signal can be affected by electrical noise, interference, distortion, weak signals, channel problems. So 1 becomes 0 or 0 becomes 1 can happen because of electrical noise, interference, distortion, weak signals, channel problems during transmission. Detection versus correction. This distinction is very important. Error detection. The receiver determines something went wrong, but it may not know which bit is wrong. Example, received data, error detected, error is 1. Error correction. The receiver determines something went wrong, and I can determine or correct the wrong bit. This is error detection. The receiver determines something went wrong, but it may not know which bit is wrong. Received data using error detector. It gets message error correction. The receiver determines something went wrong, and they can determine or correct the wrong bit. Receiver data error correction, find wrong bit and correct it. Correct it. Therefore, detection equals to find an error occurred. Correction equals to find plus fix the error. How can the receiver know something went wrong? The sender can add extra bits to the original data. These are called redundant bits. For example, suppose our actual data is 10110001. We can add an additional bit, parity bit. The receiver checks the extra bit. This is the basic idea behind parity checking. Parity bit. A parity bit is an extra bit added to data to help detect errors. There are two types. Even parity, the total numbers of ones, including the parity bit, must be even. Odd parity, the total number of ones, including the parity bit, must be odd. Example, even parity. Suppose the data is 1011. Count to the ones, three ones. Three is odd. We want the total number of ones to be even, so add it 1. Therefore, data equals to 1011, parity 1 bit. Transmitted 10111. Now there are 4 ones. 4 is even. Example, odd parity. 3 is odd, so we don't need another one. Parity is 0. Therefore, we add 0. Total number of ones remains 3 odd. What happens at the receiver? Suppose we use even parity. Sender sends 10111. Receiver counts the ones 10111. There are 4 ones even, so the receiver says parity is correct. But suppose one bit gets corrected. Now there are only 3. That's odd. The receiver says error detected. Very important limitation. Parity can detect many single bit errors, but it cannot tell you which bit is wrong, and there's an important limitation. The 2 bits change, parity may still look the correct. Example, original 10110, corrected 100110. 2 bits have changed. The number of ones can remain the same, so the parity check may not detect the error. Therefore, parity is simple error detection, not error correction. Memory trick, even parity, make total ones to even. Odd parity, make total ones as odd. That's all you need initially. Next concept, handling distance. Hamming distance, first, because it makes hamming code much easier. Hamming distance, don't let the name scare you. It simply means how many bits positions are different between two binary strings of equal length. Example, A is 10110, B is equal to 10010. Compare 10110, 10010. Only one position is different, therefore D equals to 1. Example 2, A equals to 10110, B equals to 11001. Compare 10110, 11001. Four positions differ, therefore D equals to 4. Like here, 1 is changed to 0. Here, 4 bits are changed, therefore difference is 4. Why is hamming distance is useful? Uh, it tells us how much separation there is between valid code words. Suppose a system uses three valid code words, 000 and 111. The hamming distance between them is D equals to 3. If noise changes one bit, 000 to 001, now 001 isn't a valid code word, so the receiver can recognize that something went wrong. That's the basic idea behind error detection correction codes. This is hamming distance. It is a correction tool. Here, mm, only one bit is changed. Here, only 4 bits are changed. That's why it is D equals to 4. Here, D equals to 3. 3 bits are changed. Here, if noise changes one bit, now, we discussed because of noise, some bits are may change 0 to 1. This is not a valid code word, so the receiver can recognize that something went wrong. The important formula is the minimum hamming distance of a code is dmin, then the code can detect up to dmin minus 1 errors, and it can correct up to dmin minus 1 by 2 errors. Example, dmin equals to 3, then detect capability 3 minus 1 equals 2. It can detect 2 errors. Correction capability 3 minus 1 by 2, it can correct one error. Now, hamming code. Hamming code is an error control technique. that adds extra parity bits to the original data. Unlike simple parity, hamming code can detect and correct a single bit error. The parity bits are placed at positions 1, 2, 4, 8, 16. These are powers of 2. For example, if we have a 7-bit hamming code, position 1, 2, 3, 4, 5, 6, 7. Here P1 is parity bit, P2 is a parity bit, P4 is a parity bit. Here D1, D2, D3 is equal to data bits. So 3 parity bits and 4 data bits is 7 bits. By your parity bits placed at 1 to 4, right? This is the clever part. Each parity bit checks a particular group of positions. For a 7-bit Hamming code, P1 checks 1357, P2 checks 2367, P4 checks 4567. If only one bit corrupted, these parity checks produce a pattern that tells us which position contains the error. That's why Hamming code can correct a single bit error. The big picture simple parity detects errors can't normally locate the wrong bit. Hamming code multiple parity checks, locate wrong bits, flips that bit correctly. So this hamming uses uh, multiple parities. Here you can see the hamming uses. For example, if you have 7 hamming code position P1, P2, P4, P3 are normal data bits. These are three parities you are placing. Why are parity bits placed at 1 to 4? Here 1, 2, 4, 5. 1, 2, 4, I do. If I write it now, that 1, 2, 4, right? 1, 2, 4 he said. So P1 6 1, 3, 5, 7. Here P1 6 1, 3, 5, 6. Here P1 6 1, 3, 5, 7. So P2 checks 2, 3, 6, 7. P2 checks 2, 3, 6, 7. If one bit is corrected, these strategies produce a pattern that contains full position contact error. That's why Hamming could correct a single bit error. Okay. And a huge amount of time doing complicated Hamming photos unless you're exam numerical problem. So the Hamming distance, Hamming code, digit, parity position. Okay, we'll stop here. We'll study later.